Hello and welcome to this overview of a part of our research in the group of Professor Judith Driscoll at the Department of Materials Science and Metallurgy at the University of Cambridge. My name is Markus Hellenbrand. I'm a postdoctoral research associate in the group, and today I will be talking about our efforts to realize new energy-efficient computer memory. For this, I will first provide you with an introduction as to why this research is important. Then I will convey our concept, how we try to realize this, and finally I will introduce you to some of the practical aspects of our work. We live in a data age. We're all accessing and generating information and thus data every day through our smartphones and computers. This can be in the form of online shopping, using search engines, social media, streaming platforms, and so on. And while we often say all this information is somewhere on the internet or in the cloud, in the end, the data has to be stored somewhere physically. These physical places where the data is stored are called data centers. They're large buildings crammed full of computers, and we can find them all around the world. Here is an example for Google where they store their cloud and their online services. And you have to add as many points for all the other major internet companies, such as Facebook and Amazon. So you can see that we have so many computers all around the world to host the information on the internet, and all of them, of course, consume energy. In our current memory technologies, this data storage is often not very efficient. It is estimated that today the use of data centers alone consumes as much electricity as about 20 nuclear power stations can generate. And as we can see in this figure here from a study from 2015, the use of data centers is just a part of the total energy consumption due to information and communications technologies, in short ICT. Furthermore, even without looking at the exact numbers, we can see that the expected electricity consumption will increase rapidly over the coming years. So it's estimated that by 2030, up to 30% of worldwide electricity consumption will be due to ICT. In a worst case, this could even amount to up to 50%. So it's clear that we have to do something to flatten this curve. And related to our research, this means finding more energy efficient hardware, and in particular, more energy efficient memory technologies. Before I show you how we're trying to achieve that, let's first take a look at where these inefficiencies come from. So let's take a look at the memory architecture in today's technology. I will illustrate this with the example of a personal computer, such as many of us might have at home, and it will be the same in servers and smartphones, just on different length scales. So if we open up a computer, the first thing we will encounter is a circuit board such as this, where all the other components of the computer are mounted. So in a sense, this is the backbone of a computer. Then in today's technology, we typically have three different levels of memory. The first one is closely related to the processor, which in a sense is the brain of the computer. This is because all computations and thus processes are carried out on a hardware level in this unit. So if you work on a text document or edit pictures, on a hardware level, this will be carried out in some form of processor. Now, closely related to processors, we have this first level of memory, which is called cache. It consists of static random access memory, and this is the fastest type of memory that we have in today's computer architectures. You can see, if you compare the timescales of operation, that if a processor operates faster than nanoseconds, the cache is only closely behind. So the next level then of memory would be called the short-term memory of the computer, the main memory, and this consists of dynamic random access memory. Again, in terms of timescales, it is just a little bit slower than the cache. Finally, we have the long-term memory, which is where films and pictures and profiles and everything is actually stored for the long term. So this uses technologies such as flash, and you can see that the operation timescales are very different. The difference between 10 nanoseconds and 1 milliseconds, where this long-term memory storage operates at, is a factor of 100,000. And this is the first source of inefficiency in today's computer architecture. Often it is called memory bottleneck. Now, any data that we want to do something with, such as just watching it, such as a movie, or editing, such as a picture or a text document, first has to be loaded from the long-term memory into the short-term memory. And because of this large difference in operation timescales, for much of this process, the fast memory will just sit idly, not doing anything, but it still consumes energy because it is powered on. This is the first source of inefficiency in today's memory architectures. Even worse, the memory in these fast memories is what we call volatile. So that means if we switch off power, then all information in the fast memory will be lost. And even worse, it is not only lost if we switch off the power, but it leaks away constantly. For the long-term memory, on the other hand, where the information does not disappear, just think of a USB stick. If you plug it out of the computer, the information will be maintained. However, it requires much higher energy to write the information into this long-term storage in the first place. So we have this trade-off, which is the second source of inefficiency, which is that fast memory is volatile, whereas non-volatile memory is slow and requires high energy. So what we would like to get around this problem is an ideal memory, of course, which is fast but non-volatile. And this is where our research is aimed at. This is often called storage class memory, or more generally, emerging non-volatile memory. And in the coming slides, I will explain to you how we try to realize this. Now, to really understand where the inefficiencies that I just explained come from, we have to go deeper into the technology and look at the device level of memory. Each memory block, such as the long-term memory, short-term memory, and the cache, actually consists of millions and millions of individual devices. If we start with the short-term memory, one device inside the memory block looks like this. So it consists of a transistor and a capacitor. And the capacitor is where the information, thus the data, is actually stored. Now, computers use a binary alphabet. That means they store any form of data in just two symbols. It is 1 and 0. So if we put charge on the capacitor, we can identify this as 1. If we remove charge from the capacitor, we can identify this as 0. And this charging or discharging of the capacitor is achieved via this transistor, which in this case acts as a switch. So it is either open, that means no charge can be added or removed from the capacitor, or it is closed, that means charge can be removed or added to the capacitor. Now, charge, if it is stored in a capacitor, has the property that over time it leaks away due to different effects. And this is where the volatility comes from in the case of this main memory, the short-term memory. Very similar in the cache, the fastest memory, you see that the circuit of an individual memory device looks more complicated than in the case of the main memory, but the principle is the same. Now here, the charge that we need to represent information, 1 and 0, is not stored on dedicated capacitors, but instead it is stored on the intrinsic capacitances of the transistors. You can see that the symbols are somewhat similar, and this represents that the functionality is not very different either. So we can store charge either on this dedicated capacitor, just represented by the two parallel lines, but we can also store charge on the intrinsic capacitance in the transistor. Again, we see the two parallel lines. Because of this, just the same, over time, charge will leak away from the transistors and thus be lost. Again, this is a volatile form of memory. The long-term memory then is a kind of combination of the two, in the sense that it combines a transistor and a capacitor. So the capacitor here is integrated into the transistor, as we can see by the three parallel lines now. Now we have the second trade-off that I mentioned before, that if we want to store something for the long term, it requires much higher energy to do so. This is a general principle in science, kind of, that if you want something to be there for a long time, that is, you want it to interact with its surroundings very little, you need higher energy to put it there in the first place. And this is what's happening in the long-term memory. So in order to store the information on this combined intrinsic capacitor, we need much higher voltages than in these two cases, up to more than 20 volts, which is high in computer operation. And then again, what we would like in the end is a combination of the positive aspects of all these different memories. So we want a simple device architecture, such as in the main memory. We want it to be fast, as in both the main memory and the cache, but we want it to be non-volatile, as in the case of the long-term memory. Now, technology has advanced so much that the devices that I just talked about, transistors and capacitors, are so tiny that their thickness amounts to just a few atoms next to each other. So in order to work at such length scales, we have to understand the properties of individual atoms. Now, everything is made up out of atoms. The screen that you're watching at the moment is made up out of atoms. We ourselves are made up out of atoms. But at these larger length scales, the properties of individual atoms usually don't matter anymore. They do, however, at the tiny length scales of memory devices. So atoms are made up out of a nucleus, which carries a positive charge, and a surrounding cloud of electrons, which carries a negative charge. Depending on the energy of the electrons, these clouds take different shapes, just as indicated here. And here on the right, we see that in each atom, there are many different energy levels for the electrons. From a fundamental principle that we know from atomic physics, the Pauli exclusion principle, we know that electrons cannot have exactly identical states. So that means they either have to have different energies or they have to have a different location. So that means the cloud of the electron will be in a different place and shape. So for individual atoms, this is guaranteed just by assuming different shapes of these clouds. So they can look like this or they can look like this. But if we bring different atoms close together so that these clouds of neighboring atoms will overlap, it means that now their place, their location is similar, so that the energy has to be different. So that means if we bring different atoms close together so that their electron clouds overlap, it means that the energies, so this figure here on the right, they shift a little bit up and down to fulfill the Pauli exclusion principle. Schematically, this will look something like down here to the right. So if we take individual atoms, bring them close together so that their electron distributions overlap, the energy levels will shift. And if we bring together many electrons, then these energy levels will shift and be so close together that effectively they form a continuum, which is illustrated here to the very right. Now, the shifting of energy levels happens in a way that we get what we call energy bands. So we have regions of continuous energy levels, then we have regions of gap states before we encounter the next energy band. And this is important for electronic conduction. So all the information is made up of charge, as I explained before, and in order to move charge, so in order to generate electric current, electrons have to move through a material, and that means they have to move from one atom to the other, to the next, and so on. And this movement only happens in the topmost energy band in a material. This is called the conduction band. This makes life easier in a sense because we can disregard all the energy bands that are lower than the conduction band and only focus on this one. So on following slides, you would see that I draw only the edge of the conduction band. So to summarize, atoms if getting close to each other, will form bands in energy where electrons can move, and this is where the conduction of charge and thus the transmission of information and data happens. With this, we can now start assembling the different pieces of information and understand how we are trying to realize new and energy efficient computer memory. So on an atomic level, materials can have different configurations. For example, they can be in an amorphous state, such as illustrated here to the left, where there is no order between the different atoms in the material. Or they can be in a crystalline shape. Now, when thinking of crystals, we first might think of jewelry and diamonds cut into shapes such as this one. And indeed, this is an example of crystalline materials. However, it is a much more general principle and just means that on the atomic level, the order of the material is very regular and repeated, such as we see in this schematic here. So we have a stark contrast between amorphous and crystalline materials with no atomic order at all, or a very nice and regular order. And this crystalline structure is what we're trying to use to make more energy efficient computer memory. So first of all, we have to make sure that we can achieve such a nice and crystalline structure. And we can do this in our laboratory with a technique called pulsed laser deposition. So this is how our lab looks like, and what we need for the pulsed laser deposition is the orange box in the back, which is the laser, and a vacuum chamber here in the front. And if we look into the window of this vacuum chamber, we see the process happening as in this zoomed in version here. So what we're doing is that we shoot high energy laser pulses onto an amorphous target, so a disordered material, such as here on the left, and the high energy of the laser will evaporate part of this material into a plasma plume. You can see this in the photograph here on the right. And because the chamber is evacuated, this evaporated material can travel over to a substrate on a heater here. So you see the orange glow, which means it is at a very high temperature. And by controlling the conditions inside the vacuum chamber, so the pressure, the energy of the laser, the distance between the target and the substrate, and so on, we can make the atoms arrange themselves into a crystalline material. Now, it is very difficult to make a perfect crystal. So typically there will be what we call defects in a crystal. So the materials that we're looking into are mostly oxides. That means combinations of some material and oxygen. So in this example, oxygen would be the red one, and the other material, whatever it may be, are the gray circles. And one of the most common defects in oxides are so-called oxygen vacancies. So that means in the atomic lattice, in this nice crystal, there can be places where oxygen atoms are missing, and these are oxygen vacancies. And it is very important for the quality of the material and also for the functionality of the memory devices that we're trying to make to control the number of oxygen vacancies. This is one of the challenges of research, to get the conditions inside the vacuum chamber right to control the amount of oxygen vacancies. And with this, we finally arrive at the central slide, which explains how we are trying to realize new energy efficient forms of memory. So first of all, the device layout, so the individual device inside a memory block, looks something like this. We just have two electrodes, so two electrical contacts, and between them we have the oxide deposited by pulsed laser deposition, as I explained on the previous slide. And this checks the first box on our wish list, namely we want to have a simple device layout. So this is fulfilled by this here. So how can we make a memory device now out of the different ingredients that I talked about? First of all, let's look at the atomic structure of the oxide again. So if we have a crystal with a certain amount of oxygen vacancies, then these oxygen vacancies can actually move around inside the crystal. This is because the bonds between atoms in this lattice have a certain strength. So by providing energy to the atomic lattice, we can break some of these bonds, and atoms which previously were fixed can move to a different place, such as illustrated here, so moving from up here to down there. Consequently, the oxygen vacancy, which previously was down here, effectively moves up here. So by moving atoms around, in effect, we can also move oxygen vacancies around. And the energy required for this can just be supplied by applying a voltage to our simple structure. So let's say we put a positive voltage to the top contact, we would be down here then. This means we push the oxygen vacancies to one side. If we apply a negative voltage to this contact, we draw the oxygen vacancies to the other side. Now the direction of the movement of oxygen vacancies is related to their charge. If you remember from one of the previous slides, inside an atom, the nucleus of an atom carries the positive charge and the surrounding clouds of atoms, of electrons, carries the negative charge. Now different elements such as oxygen or nitrogen or whatever you can think of, they attract or they bind the cloud of electrons to the nucleus with different strengths. And by combining certain materials, oxygen and something else, the oxygen vacancy carries a relative positive charge because the surrounding atoms attract electrons stronger than the oxygen vacancy. Okay, so this is where the directionality of the oxygen vacancy movement comes from. Positive voltage on one side pushes away the oxygen vacancies which also carry positive charge. Negative voltage at the same interface draws the positively charged oxygen vacancies towards them. So we can shift between two states here. We can accumulate oxygen vacancies at one of the contacts, or we can deplete oxygen vacancies from the same contact. And again, from previous slide, computers use a binary alphabet, so zeros and ones, and we can just identify these two distributions of oxygen vacancies with these two states. So accumulation of oxygen vacancies can be identified as state 1, and depletion of oxygen vacancies can be identified as state 2. So the last thing that we need then to make a memory that we can actually use in a computer is the interaction of these two states with electronic conduction, because computers operate on electricity. So we need electronic conduction to identify what state we're in here. For this now, we need the shape of the conduction band in this structure that I introduced on one of the previous slides. So if we go through our device structure from the top to the bottom, we have, let's say, a metal, we have the oxide, and then another metal. And the edge of the conduction band will look different inside different materials. So in one of the metals, if we start with an arbitrary level here, if we then go over to the oxide, the edge of the conduction band will be much higher than it is in the metal. And when we come to the second metal, it will be lower again. And this means that when going from the top to the bottom in this structure here, electrons will effectively face a barrier from one metal to the oxide and then back to the other metal. So again then, electrons or electronic conduction just happens above the conduction band. So we can disregard anything that happens below these edges here and just focus on what's happening above it. So electrons in one of the metal face this barrier, and depending on the height and the thickness of the barrier, more or fewer electrons can get from one side to the other. So now by controlling the accumulation or depletion of oxygen vacancies on one side of this barrier, we can modulate its height. So if we accumulate positively charged oxygen vacancies on one side of the barrier, the height of this very same barrier will be lower than in the case of depletion of oxygen vacancies. So then we can tie these two together. By accumulating oxygen vacancies, we lower the height of the barrier, which means more electrons can get over it. And by depleting oxygen vacancies from the interface, we increase the height of the barrier so that fewer electrons can get to the other side. And this is now how we relate the configuration of the oxygen vacancies to electronic conduction, and thus to a readable state of information in a computer. So we can say now that if we have a larger current, so more electrons getting over the barrier, this is our state number 1. And if we get fewer electrons over the barrier, this is our state 0. And again, here we have the binary alphabet that we need for a computer to store information. Now, for a computer to operate, this has to be reversible very many times. So we have to be able to move the oxygen vacancies back and forth throughout the materials millions and billions of times in order to get a reliable memory for a computer. And initial measurements that I carried out are illustrated in this figure down here. So you see the number of cycles where we move the oxygen vacancies back and forth from the interface. And as a function of that, the resistance, that means the measured current, so the height of the barrier effectively. And we see that we can repeat this here at least 10,000 times. Then it took too much time to measure it even further, but it looks like the states are very stable. So by switching back and forth, we always get back to the same resistance in the high and the low resistance state. So this is very promising. And the combined conduction of oxygen vacancies and electrons can be illustrated in a more complete figure here, where we measure the total current on one of the contacts as a function of the applied voltage. So if we apply a positive voltage on the top contact M1, it means that we move away the oxygen vacancies, so they accumulate on the other side on M2. This means we lower the barrier, we get a higher current. If we then go to negative voltages, first we still have the high current, but with increasing negative voltage, the oxygen vacancies are again drawn towards the contact M1, and this means the barrier will be increased, and consequently the current when going back will be lower. So this would be the total picture of the switching. And again, this is the central slide which explains how we are approaching new types of energy efficient memory. And the significant difference here is that if we remember from when I explained current memory technology, that the information was stored in terms of charge stored on a capacitor, and this charge leaks away. Now, on the contrary, while charge is involved here, we store the information in the resistance state of this structure here. So the position of oxygen vacancies either close to the interface or away from the interface. This is very different from storing charge, because the charge in current technologies is stored in the form of electrons, which can move around very easily, whereas oxygen vacancies, if you remember, they require more energy to break the atomic bonds and to move them throughout the oxide. So this is this new approach that by moving around oxygen vacancies, we store information in the resistance state of such a cell instead of the stored charge itself. Now, beside this approach that I just explained, there are several others, and I will just briefly outline some of them here, because it's very important to follow different approaches at the same time in research, because we never know which one will work out in the end. So the one that I explained is encased here in green. It would be called interfacial switching, because as I explained, the interface between one electrode and the oxide is critical for realizing the resistance state. In order to control the resistance state, we have these channels. So remember, we combine different materials, one with good conduction of oxygen vacancies and one with good electronic conduction. Now, in contrast to that, a different approach would be called filamentary non-volatile memory. it uses the same basic cell, so just 2 electrodes with an oxide in between. But here the resistance is now not controlled by the interface, but instead by a filament through the material. This is typically realized by oxygen vacancies as well, but instead of accumulating them at one interface or depleting them, they form a conduction path from one electrode to the other. And in this case, again, we can realize a state 0 and the state 1. So if this filament is disrupted and not complete from one electrode to the other, the current flowing through the device will be low, and we can identify this as a state 0. Whereas if the filament is formed, we get a higher current, so we can identify this as a state 1. The challenge with this approach is that the formation of these filaments is rather random, because while we can break bonds between the atoms and thus make oxygen vacancies move around, we cannot control exactly which of the bonds are broken and along which paths the oxygen vacancies move. For that reason, we are following this interfacial approach, where we have predefined paths of oxygen vacancies, so they will not move inside the second of the materials, but just inside the pillars that we make inside this matrix of the other material. And our hope is that by this we can reduce the variability and randomness in this other approach. Another very popular approach besides these two is making use of the difference between electronic conduction in a crystalline and an amorphous material. So if you remember from one of the previous slides, the atomic configuration inside a material can be crystalline or amorphous, and the electronic conduction in these different states will be different. So let's say we have a higher electronic conduction in a crystalline material and a less electronic conduction in an amorphous material. So then by changing between the two states, we can again represent our 0 and our 1. This is typically induced by heating up the material locally. So you can see if there was a heater down here, we can crystallize the material going out from this heater and thus change the electronic conductivity between the two states. And finally, another example, these are not all of the approaches being followed, but one that we are investigating as well in our lab, but which I will not talk about more today, is based on ferroelectricity. So this is a materials property where polarization inside the oxide can point in different directions, so either up or down. And the direction of this property, called polarization, also determines the height of the energy barrier. So think of the slide before. As we say, if the polarization points in one direction, the energy barrier for the electrons is high. If it points in the other direction, the energy barrier is low. And once again, we can represent our two binary states that we need for storing information in a computer, state 0 and state 1. Now, instead of talking about the second of our approaches based on ferroelectricity, I'd like to talk about some practical techniques that we use to characterize our materials and our devices. So first of all, we use a technique called atomic force microscopy, which we can use to measure the surface roughness and the thickness of our films. Now, both of these properties are very important to guarantee uniformity. If you remember, the thickness of the oxide determines how many electrons can get from one side to the other. So we have to make sure that the film has a well-defined thickness, which is the same throughout our samples. Furthermore, if we would have a large surface roughness, again, it means from one place of the film to the next one, we would have large differences in thickness, and again, we would have very different behavior from one device to the next. And this is bad because we want uniformity and reproducible behavior. Now, this technique, atomic force microscopy, or in this technique, this very sharp tip, which you see here in the micrograph, scans across the surface, and then a laser is directed to be reflected from the top of this tip. So the laser comes in from one side, is reflected from the top, and then measured in a detector over here. So if we have a large surface roughness now, or if we encounter a step such as this one, it means that the tip will move up or down, and consequently the reflection of the laser will be detected in a different place. So from the reflection of the laser, we can calculate the height that the tip encounters on the film. So in this example, we see that the thickness of the film, so the height of the step here from the substrate where we deposited the oxide to the oxide itself, was about 40 nanometers. That means this technique has a very high sensitivity on the nanometer level. So with this, again, we can detect the roughness and the thickness of our film, but of course we also want to make sure that we have the correct composition. So for example, the correct number of oxygen vacancies and first of all, the correct composition to begin with, so that we just have oxygen and the other component that we want instead of some foreign atoms that we do not want in the film at all. For this, we can use X-rays. So this is similar to when you have been X-rayed at the doctors, that we shine X-rays onto the sample, and depending on what is left from the signal after encountering the sample, we can calculate different properties. So in the first case, we measure the diffraction angle. If we have a nice atomic structure which is very regular, again, remember one of the slides before, and incoming X-rays encounter this crystalline structure, they will be diffracted at a certain angle which depends on the distance between the atoms. So by measuring the diffraction angle, which is called 2 theta here, we can measure the distance between atomic layers. This is illustrated in the figure down here. So we measure the intensity of the diffracted beam as a function of the angle, and you can see that for some angles there is no diffraction at all, whereas for others we get very high and very sharp peaks. And again, from the location, from the position of these peaks, with respect to the angle, we can calculate the distance between the atoms, and thus what kind of crystal we have. So again, in this example, the distance between the atoms was measured to be below nanometer, and again, we have a very good resolution with this technique. A second approach, also relying on X-rays, is that we shoot X-rays with much higher energy into our sample, and this high energy now can kick out electrons from individual atoms, and by measuring the energy that these electrons have after being kicked out, we can calculate what kind of atoms we have inside the crystal structure. So remember again that depending on the element, as I explained before, electrons will be bound to the core, to the nucleus, with different strengths. And thus, by measuring the difference between the incident X-ray energy and the outcoming electron energy, we can calculate how strongly the electrons were bound to the nucleus, and thus which atoms we have. And then by combining these two, we know what kind of crystal structure we have, and we know what kind of atoms we have inside the crystal structure, so we can have a very good idea of what kind of material we deposited. So once we're sure that we deposited the film that we intended to deposit, we can measure the electrical characteristics, so in how far we can store information in our film. This we do in an electrical probe station. So again, a view into our lab here, and if you look at the inside of this box, we see that we have a microscope with an arrangement of electrical contacts down here, and if we look through the microscope, we can see our individual memory devices that we made. So each of these circles represents one memory device. It is just a metal, and if we look at the cross section, so going into the screen, so to say, then we have the device structure that I pointed out before. So we have one electrode in the top, which is denoted by platinum pads here. In red, we have our oxide, which actually does the switching between two information states, and then we have the bottom contact, which now here is the substrate. But in general, remember, we just have three different components: one top electrode, the oxide, and one bottom electrode. So now by applying a voltage to this top electrode here, we can measure the IV curve that I explained before. So we have the current through the device as a function of the voltage, and by applying a positive voltage, we distribute the oxygen vacancies on one side of the device, which gives us a certain current level, and by reversing the voltage, we move them back from the interface and we get the other resistance states. So again, our binary state 1 and 2. And repetition again, just a different figure here. So we can look at the resistance. That means the current flowing through the device and how often we can switch it, so the number of switching cycles. And again, you can see that we can switch between two very distinct states at least 10,000 times, and it looks very stable, so probably we can switch many times more here. We do this by applying a voltage to the top contact here, as I mentioned. Often this is realized by a custom-written measurement program, and the way that a computer operates is by just putting a short positive pulse or a short read pulse to one of the contacts. So we try to do the same in our measurements. We apply, let's say, positive right pulse. So in the IV curve, this would be somewhere here. We switch the state, and then with a very small voltage, we measure what state the device is in at the moment, and then just repeat this tens of thousands or millions of times. Now, the final steps in our research on computer memory, of course, would be to get this technology from the laboratory to consumer devices. This is a very long road indeed. So the level that we can work at in the lab is individual devices, as I just pointed out on the slide before. We can maybe combine a few tens or hundreds of them into larger arrays and see how they perform then. But in the end, as I mentioned before, in our computers, our phones, in servers for data centers, there will be millions and billions of devices connected to each other and working together. Now, to realize this, first of all, we have to show that individual devices perform very reliably and fast. So this is the characterization just on the slide before. For individual devices, we have to show that they can switch between our two states millions and billions of times. As a next step then, again, we can combine them into simple circuits, but if we go beyond that, typically we would have to collaborate with industry partners, so established companies which have the facilities and the means to make more complicated circuits. So we would then have to demonstrate that on a larger circuit level, we can have tens of millions or even hundreds of millions devices working together in a circuit such as illustrated here by these schematics. And then finally, if this looks all well and good and the technology is reliable, then as a final step, some large industry partner would take over and initiate large-scale fabrication of this technology and these devices so that everyone can in the end buy them. And with this, I conclude my overview of our research into new energy-efficient computer memory. In the beginning, I pointed out how important it is to find such new technologies, because in current ICT, the global electricity consumption is expected to increase rapidly and could amount to up to 50% of worldwide consumption by the year 2030. So in order to protect our climate and to flatten this curve, we have to find more energy efficient technologies. From beginning to the end, so from materials level to consumer devices, many different disciplines are involved in this research, from physics, chemistry, materials science to engineering and IT. And among all the different approaches that are being followed worldwide, the ones that we are looking into are the use of combined ionic and electronic materials. So this was the control of an energy barrier by moving around oxygen vacancies, and the second one ferroelectric materials, which I did not elaborate more, but which follows a similar approach, moving atoms to realize energy-efficient computer memory. Finally, I'd like to thank our funding agencies. I hope you learned something, and thank you very much for your attention.